During the 1965 International Conference on Crystallography held in Melbourne, the opportunity was taken to record some of the great figures in the history of this subject. The twin topics forming the discussion basis for the conference were electron diffraction and the nature of defects in crystals. Among the distinguished scientists present, many had made special contribution to the research on those topics, had in fact pioneered a place for themselves in the story of crystallography. Dame Kathleen Lonsdale, president of the Melbourne Conference, worked under Sir William Bragg and in association with Sir Lawrence Bragg for a number of years. She was the first woman to become a vice president of the Royal Society and has contributed much to the study of crystals. Professor P.P. Ewald, a mathematical physicist, was one of the very first to work in the field of X-ray crystallography, and in fact crystal physics as a whole. Professor Guinea, who showed that a certain kind of defect in metal crystals, now known as a Preston-Guinea zone, was capable of increasing the strength of the metals very greatly. Professor Blackman contributed to the theoretical aspects of electron diffraction and to the understanding of how material of one kind can settle on and grow upon the surface of a crystal of another kind. Professor Busch was one of the first to make an electron microscope after it had been invented by Ruska in Germany in the 30s. Professor Miyake, with Professor Ueda, one of his early co-workers, has helped to establish Japan as one of the leading centers in both electron diffraction and electron microscopy. Professor Perrier is in charge of the 2 million volt electron microscope at Toulouse, France, which is breaking new ground. Dr. Boas of Melbourne is a pioneer of metal physics. In the 20s and 30s, he helped lay the basis of much of the present-day work on defects in metals. Professor L.H. Germer, the co-discoverer of electron diffraction in 1926-27. He has recently made fresh advances in low-energy electron diffraction, which is assisting research into catalysis. Dr. Garrod was chairman of the committee which planned the rather unusual theme of the conference. He uses electron diffraction to probe into defects in crystals of metals.
Metallurgy, biology and so on all tend to turn to crystallography these days, and a study of the defects in crystals for clues to some of their own particular problems. Electron diffraction and electron microscopy are being applied with very great success, I think, to a study of, for example, defects in metals. And we've therefore brought together here in Melbourne those whose prime expertise is in electron diffraction with those whose main interest is in the nature of defects, so that the ensuing discussion and cross-fertilization may accrue to mutual benefit. I think that's the real point of this conference.
Of course, most people don't know what crystallography really means. It's a bad name in a sense, because they either think it has something to do with fortune-telling or else that it's some branch of theology. But what it really is the study of solids. Now, anything that is solid, therefore, is a subject for our research, and that applies to the solids that we're made of, our own bones, our teeth, the crystals that grow in our bones and that cause us so much discomfort, or that grow like this in our different organs, kidney stones, gallstones, bladder stones. All these are crystalline in the sense that if you take the tiny particles of which they're made up, the atoms and molecules are regularly arranged inside them, of course, on a very minute scale. Things that grow in our body that are solid, they're the subject for a crystallographer to examine, or the things that a woman uses in the kitchen, saucepans, they're made of metals, which are made of small crystals conglomerated together, or the things that we eat, like salt and sugar, or the things that we have in our medicine cupboards. Even penicillin, of course, can be formed as crystals. And one of my colleagues, Professor Dorothy Hodgkin, got the Nobel Prize last year for her studies of the structure of penicillin and of vitamin B12, which is so important in the sheep rearing industry in Australia. I'm very proud of that, because actually women have been traditionally interested in this particular subject, partly, I'm sure, because the patterns, the X-ray patterns that we obtain from these materials and that help to tell us just what the substances are made of are really very beautiful. Now, this is one that I've been studying, and I think it's rather a lovely pattern, don't you? I think it's aesthetically satisfying to be able to derive information from a pattern like this that is going to be useful to people. Of course, it wants a lot of mathematics, and a lot of people are not very fond of mathematics, but nowadays the high-speed computers can do a great deal of that for us, and in fact, crystallographers, I think, are one of the major customers for computing time. Here's another pattern that is not the same at all, but which is in fact the pattern obtained from a kidney stone from a little girl in one of the London hospitals. Well, I say that they're aesthetically satisfying. Some of my X-ray photographs have actually appeared in books on art. One at least was used as a design for a rose window by a very famous architect, so that that's really quite another side of the work.
In the early days of this work, it greatly needed a sound mathematical framework, which was to come from P.P. Ewald, a young student in Munich.
I'd originally intended to become a chemist. Then I changed to mathematics, because I found that chemistry was much too unsystematic to my taste, and mathematics was systematic, but after a while I found that I didn't like it too well. And then a friend of mine dragged me, so to say, in a lecture of Sommerfeld on hydrodynamics, which captured me from the very first moment. And so I stayed with Sommerfeld and did my thesis with Sommerfeld. When I came to ask Sommerfeld for a subject, for a thesis, he took out a sheet of paper on which were listed about 12 different topics in a very wide range of subjects. And quite at the end there was a topic to find out whether you could account for the optical properties of crystals by assuming that there were little resonating particles which reacted on the light wave and which were arranged at different distances in different directions. And this topic really fascinated me, because I'd always wanted to find out something about the interior structure of the solid bodies. And so I asked him, yes. I told him, yes, I would like to take that. And he warned me he couldn't help me very much. The other topics were more of a regular kind, and he could help me. But with this, he did not really know himself how to attack it. Well, that meant that I worked for about 1.5 years before I saw the first light, and then finally by the year 1912 I had finished my thesis and was writing it up. Now in this thesis on light waves in crystals, there occurred some rather unexpected conclusions. And I wanted to check on these with Laue, who then was a junior lecturer at the university in Munich. And so I made an arrangement. Laue invited me for supper at his home. He was newly married, and we met at the institute and began walking through towards the Englische Garten in Munich to make a detour and go to his home. On the way, I began telling him of my work, of which he didn't know anything. He was astonished to hear that crystals were supposed to be built up in a periodic way of atoms or molecules or other particles, one did not know what. That was a theory which existed since, well, the middle of the 19th century and had been refined and was in a kind of final state in 1891 when Schönflies and Fedorov perfected it. But it was a formal theory, and nobody knew what were the particles which were inside the units of the crystal structure. And the next reaction of Laue was that he asked, what are the distances of these atoms? So I told him, well, these distances I cannot tell you. They vary according to what you assume to be the fundamental particles. But one thing is certain, they are extremely small compared to a wavelength of light. I do not remember that he mentioned the word X-rays, which might have given me a clue. But evidently this was the moment where he got the idea that if the atomic distances in the crystal are of the same order of magnitude as the wavelength of X-rays, then there must be some kind of diffraction effect. As far as I know, this idea was discussed at a skiing meeting which the physicists in Munich used to have about Easter in the nearby mountains, and where there were a large number of physicists coming from the neighboring universities and crawling up the slopes of the mountains in a long range and a long serpent with words like integral and light wave and quantum floating into the still mountain air, where they were heavily breathing and walking up the slopes, no ski lifts at that time. And Laue's proposal of an experiment was more or less rejected, it seems. The setup for such an experiment was all ready, because Sommerfeld was interested in the theory of X-rays and had studied the angular dependence of X-ray emission from a target. It was not very much work to arrange for a beam of X-rays to pass through a crystal and to see whether any such diffraction effect occurred. Laue and Friedrich had gone, there was a third man, Knipping, as a help to the two chief investigators, and they had gone on the assumption that the crystal would act like a reflection grating, and had put the photographic plate between the X-ray tube and the crystal, so that they would receive an outward reflection. Well, the first experiments were unsuccessful, and they didn't get anything. But then Knipping, I think, had the idea of putting a plate at the back of the crystal and seeing whether they got anything there. And lo and behold, there was the primary beam spot and surrounded by rather diffuse other spots. Then the equipment was improved. They got a sharper definition of the incident direction, and their next step was to make some of the most beautiful and unsurpassed developed Lauer diagrams of crystals. That was the triumphant end. You see, not being in Munich, I did not hear of the Lauer discovery before Sommerfeld gave a talk to the Physical Society in Göttingen. I was in Göttingen, and Sommerfeld gave this talk and showed the first pictures, and that was the first thing I heard. So I sat down that night and looked up the formulae which I'd already given Lauer in answer to his question was what happens if you take very short waves and pass them through a crystal. I told him, well, here is a formula which is strict. It need only be discussed for that case. I've discussed it for long waves. It's up to you to discuss it for short waves, and it will give you the answer. But I hadn't done it, and Lauer, of course, had not done it. So I now took up this formula and discussed it, and that led immediately to the reciprocal lattice and the sphere of reflection, the usual construction. But all this was still on the basis of a theory which was inconsistent in that it did not preserve energy. And this was a grave fault. And you could not, for this very reason, expect to obtain good intensity or significant rendering of the observed intensities by that theory. Meanwhile, war had broken out, and I had become a X-ray mechanic in the army and was sent out to the Russian frontier and was situated not very far from Dvinsk in a little barrack where I had my X-ray equipment, and no fighting was going on at the time, but there were many broken bones on account of the bad ways and roads, and so I had not very much to do. And I had a table to myself and a room to myself. I needed the table to put the patients on, and as soon as the patients were done, I took out my papers and began working at the dynamical theory. And I think without this absolute quiet and concentration which was possible during these war years, 1915 to 18, I was always on the Russian frontier there. This whole theory, I would have never managed to think out this theory. The impact was enormous. Sommerfeld made the remark to my mother, this is an interesting paper. It will never find any application, but it's very sophisticated. Well, actually, it made very little impact. There were no experiments at the time on which it could be checked. The Japanese and the Australian groups have developed the theory further to details which I had never dreamt of, which in part are only working out the theory, but in other parts are also extending the theory considerably, and especially extending the methods, so that I found a large group of people who were familiar with my theory for the first time at the Kyoto conference in 1961. I'd never before been in a room together with more than, at the utmost, say, 4 or 5 people who knew even of the existence of the theory. Although the subject was discovered in Germany, it was really developed mainly in England. It was taken up by the 2 Braggs, father and son, who had their own version of the theory, especially the younger Bragg, Lawrence, now Sir Lawrence Bragg, added a lot to the understanding of the whole phenomenon. And the older Bragg, Sir William constructed the X-ray spectrometer, and they had the great advantage of working with monochromatic X-rays, X-rays which have a definite wavelength, in contrast to the rays which were produced on a platinum target, which was then the normal target of X-ray tubes, and which have a very wide range of wavelengths, so that they do not provide the investigator with a definite scale by which to measure out the distances between the atoms. And by the use of these monochromatic X-rays, Bragg's found one structure after the other, and by very ingenious and very beautiful reasoning. They published their papers in the Royal Society, but they also published very soon, before the First World War that is, a book, X-rays and Crystal Structure, which is one of the classics of the literature in physics. It's so beautifully and simply written. Bragg, of course, had been professor in Adelaide, professor of physics, and later on in Leeds, and then in London at the University College, and finally director of the Royal Institution in London. Lower was one of the oldest among us, but he was younger than Bragg, and Bragg was, Sir William, was a kind of dominant and fatherly protector of the whole affair, and also the man from whom most of the ideas came at the time.
I began as a girl to study mathematics at the university. Then I decided that I really preferred an experimental subject, and so I took my degree in physics. And then I went to work with Sir William Bragg, who was at that time the professor of physics at University College London. Of course, he had at one time been professor of mathematics and physics in the University of Adelaide. But I worked with him off and on for 20 years. I say off and on because the off was the time when I had my 3 babies. But I had to learn a good deal of chemistry in that time, because a lot of the substances whose structure we were studying were chemical materials, and the amount of chemistry I knew when I began was very small. I was 19 when I came to work with him, but he was then 60 years of age, and he was a charming man, very thoughtful, very interesting, and he was doing very active research at that time himself. It was a real privilege to have been trained under him. Sir William and Sir Lawrence, although he was then, of course, just William Lawrence Bragg, got the Nobel Prize together in 1915, just 50 years ago. And so I suppose Sir Lawrence is one of the few men who have the unique privilege of celebrating the jubilee of his Nobel Prize. Very interesting, too, that he'd only been studying physics for 5 years when he got his Nobel Prize. He began the study of physics at Cambridge when he was 20. He had already got a first-class honours degree in Adelaide University in mathematics at 18 years, which of course was extraordinarily young.
By 1924, crystallography had come a long way. It was then suggested by Prince Louis de Broglie of France that all particles of matter might have the dual property of being both particles and waves at the same time. Confirmation of this came in 1926 from 2 physicists at the Bell Telephone Laboratories in America, C.J. Davison and L.H. Germer. They had set up an experiment to measure the secondary electron emission from a nickel surface, aiming a stream of low-velocity electrons at the nickel crystals with an electron gun. They caught the electrons coming off with a Faraday cage, which was connected to a galvanometer and could be set at different angles to the surface. When their results were plotted, they noticed a few unexpected bumps. Electron diffraction had been discovered.
started from the, I suppose, with the fact that the Western Electric Company had obtained the right from DeForest to use his valve, three-element vacuum tube. And Arnold, who was director of research, or that was he may not have held that title, but that was what he really did. He knew of this and thought that it might be a good way of amplifying speech. And up to that time, speech could not be transmitted over great distances. New York to Chicago, the transmission was very poor indeed, and you couldn't go beyond that. The distortion was too horrible. And so they bought from DeForest the right to use his three-element valve, and this was worked on. And almost immediately, the General Electric Company came out with a three-element valve too, which had a tungsten filament in instead of the filament that the Western Electric Company had, and they claimed a basic patent on it. They said that the Western Electric tube was a poor vacuum tube and depended upon the emission of electrons from the cathode by positive ion bombardment. So Davison had the job of making measurements of emission of electrons from oxide-coated platinum under positive ion bombardment, and that's the job I had. It was farmed out to me, and I did this. And actually, it was found, of course, that the thermionic emission from the oxide coating was not due to ion bombardment at all. And Davison heard of the de Broglie theory when he was in England for the first time. It had been going for a year or so before, but he didn't hear of it until then. The communication wasn't as good as it is now. And of course, the theory that de Broglie put out wasn't believed in much. It was pretty crazy at that time. But Davison heard of it and came back, and just as soon as we knew that there was a possibility that this was, the experiments went very easily. It was only a matter of weeks before it was all worked out.
The first successful experiments in transmission electron diffraction were done by G.P. Thomson, now Sir George, the son of the discoverer of the electron, J.J. Thomson. He directed a beam of high-velocity electrons through a very thin gold foil. The foil was composed of millions of very small crystals randomly oriented, so that some were tilted at the appropriate angle to diffract electrons. This diffraction contributed numerous spots in an overall pattern on a photographic plate. A South African research student, Moses Blackman, became closely associated with the work of G.P. Thomson.
I went to England actually in 1933 as a Beit scholar to the Imperial College, and there I actually continued my work on, I started at Göttingen on lattice dynamics, worked on heat properties of crystals, particularly heat capacity of crystals. At that time, I was in the mathematics department as a research student. G.P. Thomson was working in the physics department as head of the department, and he, of course, was the great expert on electron diffraction. Professor Thomson, that's George now, is really one of the old school of professors. And I think in those days, the only figure that really counted in the department was the chief. Everybody else was really a cog in the wheel. As I spent another 2 years at Cambridge doing research, again on crystal physics. Then I came back to join him as a theoretical assistant, and I was with him until he retired some 10, 12 years ago. Well, when I came to the college as assistant lecturer, and really as his theoretical assistant, he was at that time writing a textbook on electron diffraction, a theory of practice of electron diffraction, Thomson-Cochrane. Writing that textbook had raised a number of theoretical questions, and in particular he asked me to look into a relatively new theory of the diffraction of electrons due to beta, so-called what's now known as the dynamical theory. Well, I worked out some of the implications really for his textbook originally, and So I had a fair background of the theory. And when some papers, experimental papers, appeared, which suggested that the simple theory of electron diffraction wasn't quite correct, I was really in a position to rough out what is now called the two-beam theory in something like a week or two. I had all the background formulae anyway. And this really led me into what is now called dynamical theory. It's a subject I've retained my interest in ever since. I did this actually in 1938.
The modern electron diffraction camera owes a lot to Rösker's invention of the electron microscope in 1931 and its subsequent improvements. Professor Busch of Berlin was one of the workers in this field.
I came to the AEG Forschungsinstitut in Berlin. We had only magnetic lenses, and our electron microscopes had only a magnification about factor 20. And with these microscopes we began to work and tried to connect our knowledge in electron diffraction with that what we should and what we would develop, what we wanted to develop. Nobody believed in this time in the possibilities to anzuwenden, to employ these instruments. Nobody could imagine that a new world would be behind the resolution of the light microscope.
One of the people who has probed into this new world is Professor Miyake, working in the field of electron diffraction. Since 1931, working with colleagues such as Professor Ueda, he has made Japan a world leader in the production of electron microscopes and in research contribution.
And just after the discovery of X-ray diffraction by Ravel, Professor Terada and Professor Nishikawa made an important contribution in that field. And
Professor Miyake went on to describe the historical basis of electron diffraction work in Japan, and Professor Ueda pointed out that because of the relative isolation of Australia and Japan from the rest of the scientific world, international conferences such as this one are especially important.
The conference that I'm attending now, of course, on defects in solids, makes it sound as if we were examining something which was wrong, but many of the really valuable properties of materials depend upon the fact that the atoms and molecules, although normally arranged in a regular pattern, very often have a kind of disorder in that pattern which introduces electrical or mechanical properties which are useful in building or in building up electrical apparatus, transistors.
Yes, transistors just work because of that disorder in the normally regular pattern in which the atoms and molecules are arranged in the crystal. Well, these defects, as we call them, they are defects on an atomic scale. It is this disorder which we call defects, and they are of course not on this large macroscopic scale which worries engineers and metallurgists and which makes bridges fall down. The most modern technique and the most successful technique in investigating defects is electron microscopy and electron and X-ray diffraction. And that is the reason why it was so important to bring together defects and electron diffraction in this conference. Now, these defects influence properties to an enormous extent. For instance, the strength of a metal depends enormously on defects. We couldn't forge a metal, we couldn't draw a wire or roll a sheet if it were not for defects. And the high sensitivity of the photographic plate is due to defects in the silver bromide crystals in the emulsion of the photographic plate. The importance of defects was recognized about 40 years ago when one found that theoretical predictions of some of the properties were completely wrong. They were wrong by a factor of 1,000 or 10,000. And the reason why those predictions were wrong was that they were based on a model of a crystal without defects. Now, we know that there are defects in the crystal, and there are different types of defects. Well, the most obvious is the impurity. Whatever the chemist or the physicist will make of a material, there will always be some foreign atoms. And these will either replace the host atoms in their normal positions, or they will be squeezed into the crystal in addition to the atoms which are already there. They will be squeezed into interstices, and that's why we call them interstitial atoms. Now, they are, of course, the source of a disorder, of an irregularity at one point of the crystal, and that's why we call them point defects. There are other types of defects which are perhaps even more important and which are terribly important for strength and other mechanical properties of crystals, and these are dislocations where whole groups of atoms are disarranged in the crystal.
From the theoretical point of view, it's more easy to think about point defect because it is possible to calculate the properties of this point defect.
Yes.
But nature makes not only point defects but very complicated defects.
Yes.
And these defects have to be found experimentally first, because nobody from a priori could imagine such a complex defect as the zones in aluminium copper or the zones in other alloys, which are much more complicated still.
This discovery has branched out into so many parts and is so vital for the understanding of chemistry and all its implications, of biochemistry. The present great problem is the structure of proteins and of other substances which are biologically extremely important. Then for the study of metals and the properties of plasticity of metals, fracture of metals, and similar things. Then the study of catalysts, which is one of the important items in actual industrial chemistry, has been advanced greatly through X-ray research.
I suppose no scientific work lives forever, or at least only the very greatest achievements do. I think if in the course of time, I think all work disappears into a general body of knowledge and ceases to be mentioned even in textbooks. But if the consequences of that work are still used for what I'll call a reasonable lifespan, say 25 to 50 years, I think that's all one can ask.
I suppose only time will show whether the conference has been a success. We hope it has, and it certainly appears to have been so. But it's only in the light of the years to come whether we'll see whether the new ideas and the new thoughts which have been generated here, how productive in actual fact they are in advancing our knowledge in these many fields which have been presented in this conference. I think all of us who are connected with the organization of the conference just would like to extend our grateful thanks to the Australian Academy of Science, the International Union of Crystallography, the International Union of Pure and Applied Physics, the International Atomic Energy Agency. Just shows how international in flavour we are, doesn't it? And also the many governmental, academic and commercial agencies within Australia, and of course this locale here, the University of Melbourne, without whose generous cooperation and completely unstinting support this conference wouldn't have been possible. It's been very magnificent of them all.
Yes.